Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEMu. The topic for today's webinar is AISC 360 2016 Steel Member and Warping Torsion Design. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Wieland Gotzer will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within this same dialog box. If by chance we don't get to all your questions, I will certainly send you a follow-up email afterwards. So regarding the content for the next hour today, I want to quickly explain RFEMu, which is our main finite element analysis program, and the steel design add-on module concept. From here, we'll move into our first example today, and we will show you how to analyze a steel frame within the main program RFEMu. Then we'll move on to design within the RF-STEEL AISC add-on module. So for here, we have added a few additional changes with our last release. So I want to go over those today. And then we'll explain the difference between member versus sets of member design with our AISC 360 design of our beams. Then lastly, moving on to torsion, we have added a new add-on module extension called RF-STEEL Warping Torsion. What this allows us to do is to do a warping torsion analysis considering 7 degrees of freedom per the AISC Design Guide 9. So in regards to RFEMu and the AISC Steel add-on module concept, for those of you who are not familiar with our programs, RFEMu is our main finite element analysis software. So this allows us to fully model our structure. We also can integrate with BIM software such as Revit, Tekla, AutoCAD. We'd want to fully load our structure. We create our load combinations, whether that's according to a specific standard such as the ASCE 7 or the NBC, or we can manually do this, and then we can run a full analysis. Now with the analysis, we're going to get information such as internal forces, deflections, support reactions, and we can take that information and export it into our own design tools. So whether that's Microsoft Excel, we have in-house tools or hand calculations to do the further AISC design. So RFEMu is the main analysis tool that we use to start with. Now RF-STEEL AISC is a design module. This allows us to perform the ultimate and serviceability limit state designs according to the AISC. Everything is brought in from our main program, meaning I don't need to remodel my structure, redefine loads, cross-sections, materials. That's all brought in. But what I do need to define is information that is specific to the AISC standards, such as unbraced lengths. We'd also define here limiting deflection ratios to check for serviceability. And lastly, we can optimize cross-sections as well. So perhaps we'd like to use the most efficient cross-section. We can do that within this AISC add-on module. And finally, RF-STEEL Warping Torsion. So this is our brand new module, and it's a module extension, meaning you have to have the Steel AISC module in order to activate it. So everything is kind of done within the AISC module. Now, this performs the AISC Design Guide 9 for warping torsion with 7 degrees of freedom. Back in RFEMu, we're doing everything according to 6 degrees of freedom. We're going to calculate out the total normal stresses, the total shear stresses. We're going to compare this to the available torsional strengths and ultimately come up with a design ratio. And with that said, we can go ahead and get into RFEMu. So here is my, my basic moment frame. I have already modeled it for the sake of time in our main finite element analysis program, RFEM. We have our graphical window to work with here in the center. We have our tables down here at the bottom, which you can import and export directly to and from Microsoft Excel. We have our tools up at the top. And lastly, we have our project navigator. So this project navigator has all of our input information as we begin to generate this model. So for example, our cross sections are going to be available here. You'll see our materials, steel A992, and so on. So we can make quick changes to the entire model with either our project navigator, or we can graphically make changes as well. So looking at this basic moment frame, I am in a 3D environment, but I've only drawn a 2D frame here. And basic W sections, steel A992, we can see here the supports down at the bottom. Well, these are set to fully fixed. Now, by all means, we can always create a new support condition here, 6 degrees of freedom, 3 degrees in translation, 3 in rotation. We can also set a spring constant as well for partial fixity. And lastly, because RFEM is a nonlinear analysis program, you can take into account geometric and material nonlinearities. For example, with our support conditions, if we had the situation where we had friction or we had sliding, partial activity, these can all be defined with nonlinear supports as well. So for today, just keeping this as fully fixed for our moment frame. Now, I've also loaded the structure. So you can see here that I have a basic dead load applied, just 0.2 kips per feet with my upper beam here. We also have a live load, 0.1 kips per feet. And lastly, we have a wind load, a lateral load applied as a nodal load to the end of our frame here of 10 kips. So taking a look at these load cases that I've already created, you can see here my dead, live, and wind. Dead automatically includes a self-weight. The combination expressions, I've set up the program when I first started this model to generate my load combinations automatically per the AISC E7. So for this, I will see both my LRFD load combinations and my AISD load combinations. Finally, under the load combinations tab, you're going to see here all of our LRFD load combinations and our AISD load combinations. And the result combination tab is going to be something that's just an envelope solution. So it's going to give us the max and min results for all of our LRFD load combinations and max and min results for our AISD load combinations. So what I can do from this dropdown is to view all of these different load cases and combinations acting together on the structure. So here we'll see dead, live, and wind load with the applicable load factors all applied to the structure. Now, one final thing to look at before we're ready to run our analysis here in our main program, RFEM. I'm going to highlight all of my members, and I just simply double click to edit them. And we have this Modify Stiffness tab. And what I've done here is I've used this drop down. Now the default is usually set to none, but this time we have it set according to the AISC 360. So what this is doing is this is going to apply some different stiffness factors for our stiffness reductions according to the direct analysis method from Chapter C. This is in turn with the effective length method from Appendix 7. If you're using the effective length method, you wouldn't want to reduce our stiffness here and modify it in any way. But because we are designing per Chapter C, we'll have the program automatically determine what our tau sub B factor is, as well as our multiplication factors of 0.8 for flexural and axial stiffness. I did a webinar completely devoted to understanding Chapter C and how it applies within RFEM. So I want to refer you to our YouTube channel if you are interested in getting a little bit more information on that. So for now, just know that we are designing per Chapter C, so we are going to apply those stiffness reduction factors. So now we're ready to run our analysis within RFEM. And what I can do is just go to Calculate, Calculate All. You can see it solves fairly quickly here. We're running through our load cases and load combinations. Load combinations are automatically set to a nonlinear analysis considering both big P delta and little p delta. So once we're done with our analysis, you'll see here our results tab is available within our project navigator as well. We can take a look at the deflections, for example. We can scroll through the different load combinations and see how our structure is reacting under the applied loads. Now, deflections are something that we're certainly interested in, but we're also interested in the member internal forces. Well, we can simply activate that within our project navigator here as well. So you can see that my member internal forces are available for axial loads, for example. Perhaps we're interested in our shear loads. We can always increase these member diagrams to make them bigger. Maybe we would like to see the bending moments, especially for our upper beam here, for our entire moment frame. Now, all of this information is available in a little bit more detail if we right-click on a member and we choose the result diagram. So you can see that with the result diagram, we can turn on and off forces and view it along the member length, all while changing to different load cases and combinations with our scroll bar up at the top. So this is the information that is available to us in our table down here. So now we're looking at the 4.6 for members, internal forces. This is our results. We can export all this information for our internal forces to Microsoft Excel with this button here. So this is what we would like to take into our own design tools if we'd like to do design by hand with in-house tools, and we're just purely using RFEM for the analysis. So that's one option. Now, the other option is, of course, to use the program to do design for us. So what I'd like to do is to make the clear distinction now, we'd like to enter into the AISC add-on module. So I go back to my project navigator here and I scroll down and I see my long list of add-on modules. So this is why we work with the add-on module concept. Most likely, you won't even touch most of these add-on modules. A lot of them are for perhaps materials you're not using for your design projects, different international standards. So it's really just pay for what you use in terms of the design. Now the analysis is all included within RFEM for all the different materials. So we can select STEEL AISC from our project navigator. We also have the add-on modules up at the top, and under design STEEL, we can choose RF-STEEL AISC. Now, when I say add-on module, it's nothing more than just this dialog box within the main program. So as I mentioned within the PowerPoint, all of my information from RFEM is being brought into this add-on module. We're just defining a little bit more information specific to the AISC. The first thing to set here would be our standard, and we have both LRFD and ASD for the 2016 as well as some older standards. So we'll choose the LRFD Design 2016 for today. The ultimate limit state design will be all of my LRFD load combinations, and my serviceability will be my ASD load combinations. So again, all of these load combinations were brought in from RFEM. I'm not having to redefine them here. I just need to tell the program, okay, here's the load combinations I want to design for. We do need to select the members we're interested in designing. So for this one, I'm going to choose my top member here, member number 3, and I click OK. Then it's really as easy as just working from top to bottom with these lists over on the left. So we have our materials. Once again, Steel A992 is brought in from RFEM. Here are my material properties. I don't need to make any changes. We have our cross sections, same concept. My W12 by 35, which was defined for my beam member up here, is brought into the program. Here are all my cross section properties. Now, intermediate lateral restraints. What this is used for when we check on this checkbox is to brace the top and bottom flange. So you'll see here we have this drop-down box here. And what I'm going to do is jump back to the PowerPoint to explain some of the updates we made within the last release. And we'll start off with this intermediate lateral restraints. So previously, we only had the option to brace the top and bottom flange at the same time. Well, we know as engineers that this isn't necessarily always the case. We may have some type of roof sheathing on top that's really only bracing the top flange, but we're maybe not even bracing the weak axis direction. We're not bracing the bottom flange. There are other scenarios where it really depends on your connection type. You may have bracing for the bottom flange only and the weak axis direction, but the top flange is free to move. So these options can now be individually set. So you'll see here we can consider both, just the upper, the lower, or user defined, and then we set the number of intermediate lateral restraints along the beam length. So why this is important is for lateral torsional buckling. We want the program to automatically determine which flange is in compression so that when we're doing our LTB checks according to the AISC, we get the correct moment capacity. I am going to jump ahead to our next table here just to quickly explain another change. So once we go back to our example, we're going to have our second table available for unbraced lengths and effective length factors for buckling. So buckling would be strong axis buckling, weak axis buckling, flexural torsional buckling. And again, previously, what we would have with these two columns is K column, but then our second column was K times L. And you can see that first option available here. And this is a little bit of a carryover from the Eurocode, and it really wasn't ideal for the AISC. What we'd like to see is just a K column, and then our second column is completely independent of this K factor, our effective length factor. So by default, now when you launch the add-on module, this will be set. These two columns are completely independent from each other. And I more so want to focus this on our existing users now who've been using AISC. You do have the option under the details to change existing models, for example, back to separate K and L factors, or to choose to move this way for any future models. The third change is a rather big one, and it has to do with lateral torsional buckling. So with member design, and keep in mind we already did this with sets of members, and we'll get into sets of members later, but with member design, we know that with lateral torsional buckling, we refer to the AISC for W shapes according to section F2.2. Well, we can see these equations over here on the right. This equation for our lateral torsional buckling nominal moment depends on unbraced lengths. We have our C sub B factor as well as a few other variables. So when we went in and we added all of these different options for intermediate lateral restraints, for top versus bottom versus user defined, what we're now going to do is we're actually not going to consider F2.2 anymore. We are going to extract this single member that we're designing. And for lateral torsional buckling, we're going to take it out from the RFEM model and we're going to run a separate eigenvalue analysis. This is an internal planar framework model with 4 degrees of freedom on either side. Now keep in mind, this is not for all the other checks such as shear or anything else. It's only for lateral torsional buckling. So when we get back into our example, what we're going to see in our buckling table is the option for K sub Z, which is effective length factor, or K sub W, which is warping length factor. And you as a user have to define your end constraints for your lateral torsional buckling in order to correctly calculate this eigenvalue analysis. Now, as for what these actually mean, I would suggest to refer to our help file. I just took this screenshot directly from the help file. What you can do is pull that open and to get a little bit more information and familiar with what exactly these settings are. But it does have to do with being restrained with displacement, rotation, and warping, and 4 degrees of freedom on either side. So ultimately, after we set that, what the program will do internally is run this eigenvalue analysis for governing stability conditions, and will eventually come up with a critical load factor, alpha critical, and this will lead us to the elastic critical moment, MCR, so our critical buckling moment. Well, this information is all given in our results for lateral torsional buckling, so you're not going to see section F2.2 anymore for member design, but rather we're going to use a much more theoretical approach to find out what is the exact lateral torsional buckling behavior before we see some type of shape such as this for our beam member. Okay, so jumping back to our example, let's explain that in a little bit more detail. Back to the intermediate lateral restraints, we want to set this to only the upper flange. Let's assume that we have some members framing into my top beam here out of plane that I didn't model in RFEM, but I 100% want to take them into consideration for my AISC design because I know I have a higher moment capacity than what I've shown back in the RFEM model. So with this, I'm only bracing the upper flange. We're going to assume that maybe the connection type doesn't brace the bottom flange at these points. And we're going to add 3 intermediate points. And you can see here we can turn off this checkbox to view it by feet. So every 10 feet, or you turn it on, you're viewing it by percentage across the entire member. So every 10 feet, we've now added that in. The effective lengths for members. So under the Details tab, we'll see here under Stability, we've added now the additional option here by factor K and member length L. That is just to keep these columns completely independent. Really not too much to think about. It's kind of what we would expect the program to do anyway. Because I am designing per Chapter C, direct analysis method, the code tells us that we can leave our effective length factors equal to 1.0. Now, again, in turn, if I'm designing per the effective length method in Appendix 7, I would want to change these to 0.8, 1.0, 1.2, however I see fit for my particular connections of my member ends. So we have here buckling about the strong axis. We'll leave this as the full member length here, 40 feet, and the program defaults to the full member length. Now my weak axis direction, I'd like to set this to 10 feet instead. I'm going to assume that those out of plane members I didn't model in here are actually going to be bracing this member every 10 feet. Torsional buckling, we'll set the same concept here, 10 feet. And lastly, we have lateral torsional buckling, and this is exactly what I just showed in the PowerPoint. We have our effective length factor here with our drop down as well as our warping length factor. And again, refer to the help file, which you can access with this question mark down here. We'll bring up the help file. It will tell you exactly what these mean. And once you become familiar with it, you'll be able to set those automatically. Now, the program defaults to 1.0, which assumes everything is restrained except for warping. Warping is free. Moving on to design parameters, these are just a few more variables that are specific to the AISC. We're just going to leave these all as the default values for now. And under serviceability data, you can see here that what we need to choose is the member, reference to member, and we can either graphically choose the member here, number 3, or we can type it into this table. The reference length defaults to the full member length, so 40 feet. If you'd like to override this, you can just use this checkbox and type in here what your reference length is. So the reference length all has to do with our limiting deflection ratio. We can access this under the Details tab, and here is serviceability. You can see that the limiting deflection ratios for simply supported is L over 360, and for cantilevers, it's set at L over 180. But you as the user can control whatever these limiting deflection ratios are. So that's what the program is going to use for this reference length in our limiting deflection ratio. The pre-camber, you can put that in here if you have a pre-camber. And then lastly, is it a beam or is it a cantilever? Then we're just simply ready to run the calculation. You can see it solves in a split second because I already have all my internal forces for my analysis within RFEM. I'm just bringing those into this add-on module and applying my AISC equations to it. So that's why it solves so quickly. We can immediately jump down to our table design by member. And so we're looking at member number 3 here. And you'll see as I scroll down, as I take a look at these different checks for member number 3, the big red arrow is showing me exactly where my controlling internal force is for that particular member. So you can understand how helpful that would be in a huge model with a lot of members. You're just trying to understand, well, okay, which member is failing or passing here and where is it failing or passing? One thing I'd really like to point out, which I think sets us apart from a lot of other programs. We're looking at member number 3 here. You'll notice that we give you the code check for every chapter within the AISC. We're not just filtering it to the max code check. So there's never any question of, okay, well, I think that chapter F should control, but the program's telling me chapter G is controlling. Well, all of that information is given to you here. And even more so for each one of these checks, all of our variables are listed here that go into those equations, and then we have all of the equation references directly to the AISC standard. So very, very transparent in where all of the numbers are coming from. But I do have some engineers concerned with, well, maybe that's too much information. Well, you can always use your filters here to filter by the max check. And once we hit that button, well, now I can see for member 3, okay, it's actually just serviceability that is giving me my 0.6 code check. But if you are interested in all the rest of the information, that is available. So out of all these sections that we're checking, 0.6 is the controlling one. We have our nice green smiley face here because he's less than 1.0. Now, remember I talked about lateral torsional buckling. So if we choose that option here, according to Chapter F, you'll see exactly what I just mentioned in the PowerPoint. We have our required flexural strength. We have the amplifier, which was determined from the eigenvalue analysis. And ultimately, we're coming up with M critical, the elastic critical moment for lateral torsional buckling, 122 kip feet. So what the program's telling me is that this is the absolute max moment that this beam can have before I experience some type of buckling behavior. And we can actually view the mode shape here for that eigenvalue analysis. So if I turn this into the graphic view for that, and I can decrease my factor here to kind of see what's going on, we're seeing that buckling type behavior for this beam element for lateral torsional buckling. And this is what the program is doing behind the scenes. So ultimately, you should get about the same capacity for according to Chapter F, but this allows us a lot more freedom and really get into the theoretical approach and determining what the actual lateral torsional buckling critical moment is based on all of those intermediate lateral restraints. So finally, we can view all this information graphically as well. So I'm technically still within this add-on module AISC. I'm just looking at my results back in RFEMu, and we can see that from the drop-down box here, RF-STEEL AISC. So right now, I'm viewing my ultimate limit design ratios, and then I can also view my serviceability, which makes sense. We have the highest deflection at the center of our beam. So that really explains the concept of designing a single member or member. Now, what I'd like to explain now is the different concept of sets of members and why sets of members can be extremely beneficial. So if we take a look at our moment frame here, and we decide we'd like to add a roof pitch. Well, what we need to do is to right-click on our member, and we need to divide it by so many intermediate nodes. And we'll just choose one intermediate node. We click OK. The program has now created 2 separate members. Well, I can easily grab this node in the middle and drag and drop it to a point a little bit higher up. So now we have this type of roof pitch here for our moment frame. The other thing I want to do quickly is my cross sections. I have W12 by 35 selected here. Well, because I've added this roof pitch, we need to increase the size of these a little bit. So again, I can just double click in my project navigator and it will change both of these members. And we can access our cross section library, which you can see here, all of the various cross sections that we have available within RFEM. So we're still within the main program here, RFEM. We're upsizing these members. These cross sections include all the AISC, the CSA for working with aluminum sections, parametric sections. This is everything that's available. For today, we're obviously working with our rolled sections, and you can see that my filters over on the left, I filtered to AISC and the latest standard. And what we would see is our entire list here of W shapes, which come from the standard. Well, what we can do instead of setting these filters every time, scrolling down through this long list, is utilize what we call a favorites group. You can activate a favorites group and create as many as you want. And this is beneficial if you have projects that you're just utilizing a handful of cross sections at a time and you want to quickly access them. So for today, these are my sections I'm utilizing for my example. And I want to quickly change these to a W12 by 50. The material is set within the same dialog box. You can see here it's still set to A992. That's fine. and I can click OK. So now we've increased the member size to W12 by 50. Now, when I divided the member, you'll notice that the program automatically understands that the load should be carried over to the second member, even though we changed the pitch here. Everything is accounted for my dead load, live load, and win load, and we can see those loads acting on our structure here. So with that said, we can go back into our AISC module and we can design an individual member here. We can design this individual member and this individual member, members 3 and 4. But rather, we can also have the option to design this as one continuous member. And that's where we need to generate what's called a set of members. So I hold down my control key to select both of these beams. I right click and I choose the option create sets of members. So now the program recognizes, okay, I need to create a continuous member here. I click OK. And now I can zoom in and I can see that there is a faint dotted line around both of my member elements here. So this is one continuous member within the program that we can actually move to design. Now, the huge advantage of sets of members in the AISC module we'll see in just a minute, but the other is that you can design continuous members not in a straight line, exactly how this is shown. And quite honestly, you could get a little bit more complicated with our continuous member as long as it's all within the same plane. So going back into the STEEL AISC module, we can double click it to access here. So like I mentioned, we can design both members 3 and 4 if we wanted, just by typing those in here. Now we'd have to pay careful attention to unbraced lengths and things like this if this truly is one continuous member. So instead, what I'm going to do is I'm going to clear out my member design, and instead I'm going to type in here set of members 1. We can also choose it graphically within the model. And realistically, a lot of this information isn't changed for my set of members. It's still applicable whether it's member design or set of members. So we have our ultimate limit state design, we have our serviceability, and then I just work down my list. My material, steel A992, my cross section is now my W12 by 50 that was brought in from RFM. Intermediate lateral restraints. You'll see that this is available here, but we still have to define it based on each individual member. So I'm going to assume for my second example here for my moment frame, I actually don't have any restraint for the top and bottom flange. So we're going to leave this completely empty. In the same sense, for my effective lengths for strong, weak, and flexural torsional buckling, I'm going to leave this as the full member length. And you can see the program automatically updates the full member length to 40.45 feet. And even in the weak axis direction, we'll leave this as such. Flexural torsional buckling, same thing. Now, when we move on to lateral torsional buckling, you'll notice that we now lost that KZ and KW factor. So why is that? Well, what the program's doing is we actually need to jump down to nodal support. So it's now added a couple of additional tables here because we're designing with a set of members versus a member. Now, there are some huge advantages to this. So rather than having the program just giving us a few options for how our set of members is going to be restrained for our eigenvalue analysis, which ultimately is used to determine lateral torsional buckling capacity, we now have a lot more options. So again, what the program's doing in the background for lateral torsional buckling, same thing as for members. For sets of members, it's extracting this continuous member here. It's pulling it out of the RFEM model completely. And we can take a look at our view here. Under the nodal supports, we need to give the separate model here, our separate eigenvalue analysis model, some support conditions. It has to be stable in order for the program to determine what the critical buckling moment is. So it automatically places these supports at both ends. And you'll notice here that it's based on 4 degrees of freedom. So I scroll in here and we'll see here we have translation in and out of the page. We have rotation. We have additional rotation about our z-axis, which if we scroll back over to the other side, these are x, y, and z prime axes that this is referring to specific to this separate model. We also have our warping restraint. So what we have with this, of course, is we can set a warping restraint at the member ends, but we also can set spring elements for any one of these 4 degrees of freedom. Where this comes in handy, if we open up this details option here to edit the warp stiffener. Well, for example, if I had an end plate to help with warping for my member here, I could easily choose it from one of these options, give it the material, give it the geometric properties, and the program will automatically calculate the warping spring for me. I click OK, and you can see it's exported back out to the table here. Now we're actually looking at this end nodal support here. Now for our case, we're going to leave this as fully free. So we're free to warp. But this is what's going on behind the scenes with these degrees of freedom for our eigenvalue analysis. Now again, this is only for lateral torsional buckling. That's all that we're using this for. If we had additional restraints along the member length, let's say we had a beam framing in here out of the page, in and out of the page at the midspan, well, we could easily choose that node here, and we could add additional lateral support perhaps, but maybe we're free to rotate. So you can see that additional support added in here. Now we don't have that for our scenario today, but that is an option if you'd like to add it along the continuous member. So you can see how powerful this can be when we have, number one, a continuous member not in a straight line, and number two, when we really want to get into the details for lateral torsional buckling of how this member is restrained or not. Now, the member hinges. The information for our eigenvalue analysis is completely separated out for this continuous member from our RFM model. So you need to tell it if you have any member releases at either end for those 4 degrees of freedom. Now, in our case, we have a moment frame, so everything is fully fixed. But if you did have a release, you would add it into this table here. As far as serviceability data, exact same concept that we saw for members, but this time we need to choose set of members. And we can either graphically select it, or we can just type in 1 into our table. Now, the default length will automatically populate here to the full continuous member length of 40.45. And we're still referring to the limiting deflection ratios under our details tab of L over 360. And then we quickly run our calculation. So the program does have to rerun the calculation back in RFEM because remember we changed our cross sections, we added the roof pitch, so it took maybe 1 second longer, but still very quick. We brought in all those internal forces into this add-on module, STEEL AISC, and we apply the AISC code equations to it. So now the only difference you're going to see is we still can view our results designed by member. So if we're interested in viewing, okay, well, what's controlling on this member versus what's controlling on this member, we can view that within our tables. But probably what we're interested in is designed by set of members. So we're now looking at this full continuous member here and our different AISC checks. So we'll see here chapter F, chapter G. Scrolling down to stability analysis, we can take a look here at the alpha critical for our lateral torsional buckling, which ultimately we come up with M critical, the elastic critical moment for LTB. And again, just like what we saw with our members, we can view the mode shape for that analysis. We can increase here the factor to see that buckling behavior. So that was what's going on behind the scenes. That's why we had to support this separate little model here in order for the program to determine what this value is. Now, just like with members, we can jump back to our graphics and we can view the code check for sets of members graphically as well. So we're looking at the ultimate limit state design, which it looks to be controlling where we have this moment connection here of the beam to the column, and then serviceability, as we would expect, is controlling at the midspan here. So that really explains the main concept of understanding members versus sets of members within the AISC standard. So the next thing we want to move on to is, of course, warping torsion. And with that, I'm going to adjust my model here just a little bit. we're going to go back to, and I'll display my loads just to show you what's going on as I change this frame. I'm going to take this second member over here, just highlight it graphically. I hit delete on my keyboard, and I'm going to grab this node at the end of my beam, and I'm just going to drag and drop it and snap it to the top of my column. You can see a lot of AutoCAD-like features which just make our life a little bit easier when we want to make small changes to our model. The load follows. We're looking at the same thing for live load, wind load, just like what we saw with our first example. Now, a couple of changes though. So we obviously need to add in a torsion load if we want to check warping torsion and such. So let's really exaggerate that here. I'm going to go back to my load cases, and we jump to the load cases tab. I create a new one, and we'll call this one torsion. The action category, maybe we set this to live. Now, under the load combinations, the program will generate a few more load combinations just simply because we've added a second live load case, and you can see those all listed here. Going back to the RFEM model, if we take a look at torsion, we need to actually apply the load to the load case, and we can do this with our tools up here at the top with a new member load. With the new member load, rather than being a distributed load over the entire member length, we're going to do a concentrated moment. This moment is going to be about my global x-axis, which I can see my axes back in my RFEM view here. And you'll notice these pictures update to kind of give you a general idea of exactly what's going on with this load you're about to apply. The magnitude is going to be 7 kip feet, and we'd like to apply it at the midspan, so at 20 feet. I click OK, I simply highlight over my member, and now we have this torsion load applied here. So what I can do then is look at all of my load cases and combinations, and I can see this new torsion load acting with the rest of my loads on the structure. So we're now ready to move on to our analysis and design. Before we do, what I want to do is to take advantage of the information that my sets of members gives me versus my member. So technically I could come in here and just design this single member like we did in our first example. But instead, although this is one member here, I can still right-click and create a set of members. And there's a couple reasons why I'm doing this. Number one, for our first example, I like the options that a set of member gives me versus a member, meaning those end restraints for lateral torsional buckling with 4 degrees of freedom. I can expand on warping springs, things like that. So although this is still a single member, we can design it as a set of members. The second reason why I'm doing it is because our module extension RF Warping Torsion, which we'll get into in a minute, is only available for sets of members. So just keep that in mind when we move on to that example today. I don't really need to worry about running the analysis here in RFEM. I can if I want to take a look at the internal forces, but by launching the AISC add-on module, we're going to run the analysis along with the design all at the same time. So what's nice is that I'm just going to keep all my information in here from the previous example, but there are some changes we need to make. Number one, we added additional load combinations for my second live load. So we want to make sure that we take that into consideration here. Serviceability limit, maybe I'm not so concerned with serviceability checks. We kind of understand the concept with that, so we'll just focus on ultimate limit state design. I am designing my set of members 1. So again, set of members versus members, we're going to move forward with set of members. And then just working down my table once more, I get to intermediate lateral restraints. Well, for this scenario, I'm going to assume that I am bracing both the top and bottom flange. And maybe my connection details, for whatever reason, will brace both of these flanges at every third point. So I've added 3 intermediate lateral restraints here at 10 feet, and then we can continue moving down our list. Effective lengths, well, for my buckling about strong, weak, and flexural, I'm going to leave this as the full member length here. So it is set at, actually it's remembering what the program had set for my last set of members. So what we can do is just to simply override this to make sure it's a little bit more relatable to our current example. So that was just carryover from our last set of members. Now, what we can do here is move on to the nodal supports for our lateral torsional buckling. And again, the program already has some suggestions here for my particular scenario. We have our 4 degrees of freedom on either side. We've already really covered this with our last example. I want it to be free to warp and to rotate at the member ends, but I've restrained it in these additional 2 degrees of freedom. And finally, member hinges. I'm not going to apply anything here. We have a moment frame, so we don't need to take care of that. And we run our calculation. So it's running through all those new load combinations, and it's applying the AISC code checks, and eventually we can take a look at design by set of members. And we see here something that's very bad. We have our sad red face because he's over 1.0. So this immediately flags me that, okay, something's not passing according to the AISC. Well, if I take a look at that particular check, I'll notice that I'm failing according to Design Guide 9, check of shear stress due to torsion and shear stresses. And I look down at my results here. It looks like I have my required shear strength. I'm also accounting for torsion here. So let me go back to the PowerPoint to explain what is happening when we're looking at torsion. Now, keep in mind, I have not activated my module extension. I'm purely doing torsion design with what's given to me within the AISC. And it's quite common, not only in our program, but many other programs, that we just simply combine shear stresses. And what we're going to do is we're going to take the shear stress due to bending and axial loads, and according to Design Guide 9, equation 4.6, we convert this into shear stresses. So you can see we're utilizing this V here, which is the shear force from RFEM. This is my internal force that I've already determined from the main program RFEM. We convert it to shear stresses. Well, on top of that, we now have torsion. So we're going to utilize St. Venant's torsion and convert our required torsional moment from RFEM into shear stresses as well. Then we're going to add these two stresses together. And we compare this to the available torsional strength from the AISC. And in our case today, we're failing. In my opinion, this is really just a quick and dirty way to combine torsion along with shear stresses so that we can get some type of design. What I'd like to do is to explain now what we would like to activate with our module extension RF-STEEL Warping Torsion. So we all know from basic FEA that the equation here is K times U equals F, with K being our stiffness matrix, U being the nodal displacement vector, and F being the nodal point load vector. This is what RFEM, our main program, is doing. However, this is according to 6 degrees of freedom. This is this case with pretty much all structural analysis software, 6 degrees of freedom. That's what we're used to. Well, with RF-STEEL Warping Torsion, instead, we're going to run a nonlinear warping torsion analysis according to 7 degrees of freedom. So we're going to add in that 7th degree of freedom for warping. Now, what happens here is the exact same thing that we saw for lateral torsional buckling with our members and sets of members. We're going to extract out this set of members from the RFEM model, and we're going to recalculate it within this module extension. Now, with that said, in the exact same way I just showed you with sets of members, we have to set a statically determinate model with those nodal constraints and member releases. The difference here, though, is that previously we were working with 4 degrees of freedom on either side. Now we have the full 7 available to us. So the next problem that we're dealing with, though, is that all of my loads and my internal forces back in RFEM were determined with 6 degrees of freedom. I can't use those anymore. We can't just easily convert 6 degrees of freedom to 7 and use the same internal forces. So we have to recalculate those as well. And underneath the hood, what the program's doing is applying theoretical calculations to convert the RFEM internal forces into new applied loads and to rerun it according to 7 degrees of freedom. And ultimately, we're going to determine those new forces and deformations from the warping torsion analysis. And this is back to basic FEA with the stiffness matrix U and F, but according, again, to 7 degrees of freedom. So it's extremely powerful what we can do all within this add-on module. So the best way to do that is to show you the example here. So we jump back to our add-on module here, RF-STEEL AISC. I'm going to go to File, and we have the option here to copy case. What this is doing, I'm going to rename this to Warping Torsion. And I now have 2 drop-downs here. I can always jump back to that design I just did according to my various code checks from the AISC. But in my second case here, I still wanted to design my sets of members number 1, but under the Details tab, we have Warping Torsion. So if you purchase this module extension, Warping Torsion, you can activate it here. The method of warping analysis can either be according to second order analysis or linear. The load application does not necessarily have to be at the shear center top of the beam. In fact, you can choose any one of these 9 points to apply the load. So we can really get detailed in terms of this warping torsion analysis. So I click OK, and you'll notice here, quite honestly, everything looks the same. So materials, we've been through this, cross sections, we've been through this, intermediate lateral restraints, everything looks the same here. I'm still going to keep this as 3 intermediate restraints for both top and bottom flange. Then we will jump down to the nodal supports. You'll notice that I no longer have the option for the buckling input that we saw with sets of members. That table is completely gone. So jumping down to nodal supports, here is the huge difference. For my end supports here of my extracted set of members into my own little separate model here, I have my 7 degrees of freedom. So this is what warping torsion is allowing us to do. So the program makes some suggestions here on applying our end restraints to our set of members, and perhaps for this nodal constraint over on the right-hand side, I'd like to release my translation in the X direction. I want this to be free to slide at this particular location. Now we do have a moment frame back in RFEM, so I'd also like to restrain all of my rotations here in the local X, Y, and Z. But we still have this sliding availability here. Now warping, in my case today, I want this to be completely unrestrained. But if we have an issue with warping, this is where we would want to go in and add a warping restraint, whether that's full warping restraint or a spring available within this dropdown. And again, these can be added along the full member length. We just have to go back in and add some additional nodes within RFEM. So now we have defined these 7 degrees of freedom at either end to make sure that this separate little model is fully stable when we run our calculation. Member hinges, we don't have any for this scenario, so we don't need to worry about this once again, and we can run our calculation. Now, one more thing I'd like to touch on, we probably don't use this so much within the AISC, but it is possible to define an imperfection with a bow. So you can set that imperfection here if you'd also like to consider that within the warping torsion analysis. So we're leaving that empty for today, and we can run our calculation. It solves within a split second, and we immediately jump to design by sets of members. And we'll notice something very, very different than our last example. We now have a check here of 0.27. This is very different than what we just saw with the torsion considerations being applied to shear stresses, and our code check was 1.02 when we kind of just do it in the quick alternative within the AISC. So we only see two different checks here when we run warping torsion. We're looking at the elastic check for normal stresses, and we also have shear stresses. The first thing to notice here is that if we take a look at our normal stresses, the governing stress point is given as stress point number 1. Well, if you're curious to see where exactly this governing stress point is, if you click this little info button, we can take a look at the various stress points. I mean, you can view them graphically here along with the numbers. We also can bring up this table, which shows all the information on these different stress points. You'll notice that for stress point number 1, well, this is at the tip of our flange. So that's what's controlling for our normal stresses for warping torsion. Then we have some additional stresses here. And again, I'm going to jump back to the PowerPoint module just to explain these in a little bit more detail. We have two different checks. I mentioned one is normal stresses. This is all according to Design Guide 9. The first thing we're going to calculate is the normal stress due to the axial loads. And we can see that from simple mechanics equation, also available within Design Guide 9 4.7. We're also going to calculate the normal stresses due to bending. And this is for both axes, both strong and weak axes. Lastly, we're going to calculate the normal stress due to warping. Again, we've added that 7th degree of freedom. We calculate it with this equation here. Then finally, the design guide says that we can use superposition and add all of these normal stresses together to get our total normal stress according to equation 4.8a. Well, once we've done this, we obviously need our available torsional strength. So this does come from the AISC equation H3-7. And for normal stress, the available torsional strength is just purely the yield strength. So once we have this information here, we compare it to the total normal stress, we divide them, and we get our design ratio. In the exact same sense, we're also checking the elastic check of shear stresses according to Design Guide 9. So we're going to first check the shear stresses due to bending and axial for both axes. Both strong and weak axes we'll see in our results. We're then going to calculate shear stress due to pure torsion. And finally, we have shear stress due to warping. And once again, Design Guide 9 tells us with superposition, we can add all these shear stresses according to equation 4.9a, and we come up with the total shear stress. Well, once again, we have to have our available torsional strength. We refer back to the AISC equation H3-8 under shear stress. The only difference here is we're now applying a factor of 0.6 in front of the yield strength. So we're comparing our total available torsional strength here to the total shear stress, dividing them, and ultimately getting our design ratio. So those are the two results you're going to see for normal stress and shear stress back in RFEM. And sure enough, as we just saw in detail, all of our different stresses are listed here. So right now I'm looking at my normal stress. I can see the equivalent equation reference from Design Guide 9 for normal stress due to axial loads, due to moment, and due to moment in both directions, strong and weak axis direction, as well as warping. We add them together for the total normal stress. We compare this to what the AISC standard tells us according to chapter H3-7, and we get our design ratio of 0.27. So you can see how this is extremely beneficial when we have torsion on our members and we run that quick calculation where we just combine shear stresses, again, which is quite common, but we're failing. Well, in reality, instead of upsizing the members, why not just do a little bit more detailed analysis and design on this with 7 degrees of freedom utilizing RF-STEEL Warping Torsion? Lastly, we can view this information graphically like what we saw for everything else. So we're looking now at the warping torsion design results. We can view the ultimate limit state design here, which we can see is controlling again at our moment connections. So that is really all that I wanted to show you for today. And as always, I know that was quite a bit of information, but hopefully you have a better understanding now of AISC design with members versus sets of members and our new add-on module extension, RF-STEEL Warping Torsion. I always want to encourage everyone to visit our website at dlubal.com for more information, not only on RFEM, but all these design modules. You can also follow us online on our social media sites. One I really like to point out is YouTube, where we record webinars such as this one, and you have free access to them all the time. We'll also give you information on events and conferences, newsletters, things like that. And lastly, our knowledge-based articles are extremely beneficial because we don't necessarily point these directly just for use in our software, but it's really on general technical structural engineering knowledge. So you can find that on our website as well. Our email at our Philadelphia office is info-us@dlubal.com, and our phone number is 267-702-2815. So if you have any questions about today's webinar or any other capabilities of the software, feel free to shoot us an email or to give us a call. We will have many more upcoming webinars. I try and do them about once a month. You can register on our website at dlubal.com under support and learning and webinars. As pretty much all of you know today, though, I send out a couple reminder emails when those webinars will occur, so you can sign up through that way as well. Many of you are wanting PDH credit for today. That's great. We're more than happy to issue that. Just a couple of requirements. Number one is that you were here for the full 60-minute presentation. This is required by the states, which we are accredited to give PDH. So if you were here for the full 60 minutes, can you please send a request to our email at info-us@dlubal.com. Again, send the request to info-us@dlubal.com. Let me know who was in attendance today, and I will send that certificate back to you. And with that said, I want to thank everyone for attending today's webinar, and as always, we hope to see you at the next one. Thank you.